Salutations and welcome to Space Time Continues. My name is Mary Louise Davey, and let's get going to space.
LD, verify, go for launch.
Go for launch. Falcon 9 is configured for flight.
Minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Liftoff of Falcon 9. Falcon 9 is over tower. Move to 39A.
Copy, we'll go.
Through max Q, which is the maximum aerodynamic pressure. You will see the difference is sent through the atmosphere. And as you can see, the main engines have cut off on the first stage. And we have a successful separation. Just waiting for that second engine to start up. Burn has begun. On the left-hand side, you can see the first stage approaching the pad. And on the right-hand side, you see the pad shot. Let's watch it land.
Warp speed is something we need if we want to travel beyond our solar system. Yes, if you recall in our episode where we discussed space propulsion, there are other methods, but they will all mean generational ships, where the ones that leave are not necessarily the people that arrive, unless, of course, we can develop glassy water. You are familiar with glassy water and the states of matter, correct? That's solid, liquid, gas. The fourth state is plasma. And there was talk of adding glassy water. What is it? Well, technically speaking, there is this striking polymorphism of ice with two different cryogenic amorphous phases. Under normal conditions, water is a liquid, but glassy water, also called amorphous ice, can exist when temperatures drop below the glass transition temperature. Now, although glassy water is a solid, its structure exhibits a disordered liquid-like arrangement. Low-density amorphous, or LDA ice, has been known to exist for 60 years. And a second kind of amorphous ice, high-density amorphous, that's HAD ice, was discovered in 1984. Polymorphic transition of ice is accompanied by a surprisingly sharp and surprisingly large volume change, more than 20%. When thermodynamic parameters such as temperature or pressure change infinitesimally, well, glass transition is not the same thing as melting. Melting is a transition that occurs in crystalline polymers when the polymer chains fall out of their crystal structures to become a disordered liquid. Not so with the glass transition. The glassy transition happens to amorphous polymers, polymers whose chains are arranged in crystals, but strewn around all over the place. So if you see where this is going, This might be the solution to a form of hibernation, the cryogenic travel. While we travel, this glassy water does allow for a certain, scientists are working on this now, and so possibly this would bring the generational ships into livelihood. However, in the meantime, let's look at warp speed. Look at the space around us. Think about the propulsion. Think about what stuff goes inside. We're going to spend a show, maybe the next one, maybe the one after that, I haven't decided just yet, but looking at all the cool gadgets that would go inside such a ship when we plan our generational ship. So we're going to plan it. But in the meantime, let's go back to warp speed for today. And maybe a primer just to make sure we're all on the same page. Okay? So, probably the most important things to travel would be speed of getting there and not achieving light speed, at least not in the conventional sense. Now, the two seem somewhat at odds with each other, no? Enter warp speed. Have you heard of loopholes? Well, they're one of my favorite things. Ask anybody. Ask my parents, because I often tick them off when I found the loopholes. But nonetheless, that's another story. But in this case, I bring loopholes up because, well, that's how we can achieve the speed of light without having to worry about that pesky Einstein. I am referring, of course, to that German-born mathematician and physicist by the name of Albert Einstein, who in 1905 came along and changed everything. You see, he published his theory of relativity, special relativity, which claimed a rather crazy concept. There is no preferred frame of reference. Everything is relative, even time. Basically, the laws of physics must be applied with equal consideration. In all constantly moving frames of reference, he further explained that the speed of light is a constant. It's about 186,000 miles per second, or 300,000 kilometers per second. His biggest thought of this was, well, it was represented by a single equation. Really elegant. The equation was E equals mc squared, where E is energy, m is mass, c is the constant, the speed of light, so you can actually count it as being a 1. It's a constant, at least in a vacuum. So according to this equation, mass and energy are the same entity and can be changed into each other. So as energy goes up, increases, mass must also go up. So this is no big deal when you're at slower speeds. But when an object gets really fast, the mass rises just as fast, and eventually the object tries to travel 186,000 miles per second, and its mass becomes infinite. And so too does the energy needed in order to make it move. So this is why no object can travel at the speed of light. But how about if you were to move at the speed of light? How would it be for you? Well, for you, there would be a slowing of time. For people not traveling with you, they would not experience the same time. Theirs would be, say, twice the amount of your time. So they'd be experiencing time much quicker, and it'd be slower by you. So, now that we're on the same page, we all know we can't travel at the speed of light, right? Well, how about that loophole then? I mentioned a loophole. Okay. Suppose we were to take the ship and place it into a bubble. Now this bubble, it's manipulating space, warping it, if you will. In front of the ship, it's contracting. And behind the ship, every bubble, it is expanded. Inside the bubble, you have successfully avoided going light speed. In fact, as long as the ship is creating its own gravitational field, the spaceship could travel locally at very slow velocities, therefore avoiding the pitfalls of Newton's third law of motion. You see, you're actually traveling, pulling the destination toward you while pushing your starting point further behind you. So all this is zooming over you, but you're just here in this bubble. In the fictional Star Trek universe, the reality of the warp speed is accomplished through the use of a warp drive. Now, powered by the antimatter reactions, think to the show that I did on space propulsion, because I explained a little bit of it there, which are regulated by a substance called dilithium. Is a strongly electrophilic diatomic molecule. Now, it's comprising of 2 lithium atoms. From this, you now have electroplasma, a type of matter which it has its own magnetic field. And that magnetic field reacts with the starship's warp coils. Now, these warp coils are enclosed in what the Star Trek universe calls a warp nacelle. This warp field, or bubble around the Enterprise, allows the ship and its crew to remain safe while space travels around them. But forget fiction. Is it actually possible to create a spaceship that would propel space travelers across nearly infinite galaxies in next to no time? Well, depends who you ask. According to physicist Miguel Alcubierre, the use of so-called exotic matter, a theoretical type of matter with negative energy, if it exists, would do the job of repelling space and time and creating the gravitational field. This exotic material, it's a strongly electrophilic diatomic molecule comprising 2 lithium atoms covalently bonded together. Li2 is known in the gas phase. Making the warp drive work would be another thing. The warp drive in Star Trek gets its power by reacting matter with antimatter. And the result is complete annihilation and the release of pure energy. Now, we discussed when we did the matter and the antimatter and how cool that would be and how great that would be to utilize something off of antimatter. The repulsion would be 1,000%. It would be great. However, there's that minor problem about the fact that we can't get enough antimatter. We can't create it. We have only created enough to barely heat a glass of tea, a cup of tea. But, oh well. Now, we were working on, NASA was working on a warp drive. And they found that they were having problems. They had an original design of the ship that looked somewhat different from what the M drive, what that ship looks like now. But when they started this out, it looked a lot different. It looked a lot like the Starship Enterprise. And then they found something cool out. They found that this thing that they were trying to create, this thing that they were pretending, it was hypothetical, theoretically it existed, and it did that bubble, but it was theoretical, but they were trying to create it. And it's kind of hard when you're trying to create something that you just think might exist, you don't know exists. Well, they managed to find it in the wild, just hanging around in space. They found this particle, this bubble-like thing, and they went, oh my gosh. And so it actually was created. But then they realized that the ship and the way they're doing things wasn't quite in line with what it should be. They were going after the Enterprise look instead of what look do we really want to have for this? What look does it need? What look makes it work better? And that was the beginning of the change. But I digress. Let me get back into the slow progression of how we get there. Although there's little chance during this century of humans developing a spaceship that could bend space, could actually bend space and travel to distant galaxies faster than the speed of light, this hasn't stopped us, scientists and fans of the series especially, to think about the potential. But that would be illogical, wouldn't it? Perhaps. But instead of calling it warp drive, we'll call it the M drive. The M drive is the Rubik's cube of the physicist. It is a hypothetical thruster come to life. Its origins come from the British engineer Roger Shaw, who claimed it could produce thrust without any propellant or fuel. See, not exactly. It's a thruster with thruster-like cone that produces momentum by bouncing around electromagnetic waves, and as the waves hit the base area, the larger end of the cone, well, the photons produce a tiny force that causes the small end to accelerate in the opposite direction. Now, in theory, this doesn't work. It kind of violates physics, really. You know that pesky little law, the third law? You know, every action has an equal and opposite reaction. Well, the drive has now been peer-reviewed, and after years and years of working on it, so perhaps the laws of physics are wrong. But I offer another option. Maybe there's something going on, but we don't know about it. We can't see it. Maybe something that involves, I don't know, something either too small that we can't see it or something we can't measure as yet. I don't think we should immediately jump to it doesn't match physics. So here's an even odder piece of data. In tests, the M drive didn't produce untold amounts of thrust. In fact, the amount of thrust produced consistently was 1.2 millinewtons per kilowatt. A small amount of thrust over a long period, sort of like the ion thruster. But they believe there may have been some error. Sources that could explain this said, well, yeah, we just developed it to see if this peer review could get it through and make it work. We didn't try and make the best machine to make it work the best it could. Now remember that the original calculations on this are that it will power us to Mars in 70 days instead of about 8 months rather. So, okay. But as I said, the team stated that they weren't trying to put out a good thrust, but just to prove that the concept actually worked. So it's extremely likely that the M drive will get far more efficient as time progresses. The next major testing field for the M drive is up in space. Since a date late in 2016, there has been mention of NASA planning to test it in space. But to date, there seems to be no record of this. However, China claims that it has already tested, as of last December, tested an M drive in space. In addition, supposedly some anonymous source told the IB Times that the US was doing the same thing on board that, you know, that mysterious space plane that flies around, the X-37B? Well, much later now, and similar rumors are still circulating, so it's been going on for quite some time, but the plane that takes off and goes around and around, and it's a spy plane or Boeing X-37, supposed to be solar powered. It's been orbiting Earth nonstop for record amounts of time. Well, supposedly that's testing an M drive. Possibly. I'm not a big conspiracy theory person, but I do find that concept food for thought. It's actually a rather interesting one. Okay, so let's assume we have a warp drive, an M drive. And cool part is, now we can leave the solar system. But then the question becomes, where are we gonna go? Well, you know what I've always wanted to do? I've always wished we had some sort of probe that was going to a black hole, say the black hole in the middle of our galaxy. What's it, V4641 Sagittarius A? I know it's a long way, like 1,600, or is it 1,400 or 1,600 light years, but at that point, who cares, you know? But maybe using a slow technology, we'd send one probe, and then maybe a month later we develop one that could go there twice as fast and we get there. So, all right, I understand why we've waited. So, but now I'm going to explain what a black hole is as scientifically accepted. And I say scientifically accepted because I have my own theory on what a black hole is. and I did calculations on it. Now, I do not believe in calculations that use a negative number or square root of a negative number. I read this book, which actually, it put my thoughts into things. The Story of the Square Root of -1 by Paul J. Naheen, which not only did I love, but I've read countless times, but it also emboldened me to do my calculations because it was like, wow, somebody else agrees with what I think. So I came up with my version of a black hole and what it is, and my calculations worked out. And it didn't have the problem that I had. I have a real big problem with the singularity they talk about. So first I will explain to you what they believe, they meaning any other reasonable person, and then I will tell you what my theory is. Okay, so this theory is by John Mitchell, Carl Schwarzschild, Jacob Birkenstein, Brandon Carter, Leonard Susskind, Don Page, Andrew Strominger, and of course Stephen Hawking, as well as many other well-known physicists. Naturally occurring black holes. Stars are massive. Our nearest star, the Sun, is roughly, well, 1.3 times 10 to the 30th, I think. In simple words, a black hole is a location in space with such a strong gravitational field that the escape velocity, escape velocity is the minimum speed necessary for an object to escape from the gravitational pull or influence of a massive body. So the escape velocity necessary to leave or escape from a black hole exceeds the speed of light. What this means is that you require a velocity greater than the speed of light. Now remember, you can't travel the speed of light, we just figured that out. So, but it requires you to travel faster than that speed that you cannot travel if you want to escape a black hole. We ask, why is it called a black hole? Well, no light can escape. And since it doesn't reflect light, it's as black as can be. Perhaps it'd be easier to think of it as a river, where the current is so strong that no matter how fast you try to paddle, you can't escape it. You can't get off to the side, you can't pull that diagonal that you pull, you can't do anything. So let's look into a black hole and how it's formed. So how is it formed? Well, first you start with a massive star. The star fuses hydrogen into heavier elements. Basically does the whole thermonuclear fusion thing. You know, thing we want to do someday here. The heat produced creates an outward pressure, which acts against the inward force from the gravity. So the thermal pressure is the only thing that keeps the star from collapsing under its own gravity. And as long as the star has fuel, and it keeps fusing, well, creating heat, doing all that, well, then it's got the thermal pressure and gravity and balance and hydrostatic equilibrium, it's all referred to. So as long as they're able to do that, that's fine. But eventually the star runs out of fuel. And now this means that the thermal pressure decreases and the gravity takes over. And this is when the core collapses. And stars with an end mass below the Chandrasekhar limit of 1.4 times the mass of the Sun, they become white dwarfs. Stars that have an end mass between the Chandrasekhar limit and the Tolman, Oppenheimer, Volkoff limit, the TOV limit of 2 to 3 times the mass of the Sun, well, they become neutron stars. And then there are stars with an end mass above the TOV limit. These become black holes. The end mass would be about 25 times the mass of the Sun. So that's heavy. Let's say the star in the image above is 30 solar masses. When the core collapses, an explosion occurs, called a supernova, which ejects a lot of the material into space. The initial mass of a star relates to its end mass, i.e. a star with an initial mass 30 times the mass of the Sun. Its end mass is around 4 solar masses. And that's enough to form a black hole. How does one determine the strength of its gravity field? Actually, for that matter, how is it formed? Thought you'd never ask. Well, the strength of a gravitational field depends on two independent factors: the mass of an object and how far away you are from the object. You see, if you look at a star from above, it has a much bigger radius than the neutron star and the black hole. While the sun has a diameter of 1.3 million kilometers and one solar mass, a neutron star is typically about 20 kilometers at about 1.4 solar masses, and a black hole with a mass of 3 solar masses is thought to be compressed to a point, though it's through its Schwarzschild radius or gravitational radius at this mass is around 8.86 kilometers in diameter. I'll touch on the Schwarzschild radius in a moment. So imagine you have 3 objects of increasing mass, but decreasing radius. Now, although all 3 objects have gravitational fields of different strengths due to differences in mass, their radius is also crucial. If we assume all 3 objects to be of the same mass, but different sizes, then in order to experience the same gravitational field from the star as from the neutron star, you would have to be inside the star. However, to experience the same gravitational field from the neutron star as from the regular star, you can be a long distance away. That's indicated by the yellow circle around the neutron star. So you see, given the same mass but a smaller radius, you can get much closer to the neutron star as you could to the regular star, and so you would experience a far more intense gravitational field on the surface of the neutron star as on the regular star. A black hole has much more mass and a far smaller radius, presumed to be a point source. So its gravitational field, when you get close to it, is really extreme. Extreme enough so that not even light, which has the greatest speed possible in the universe, can escape. What's the anatomy of the black hole? What are the various components of the black hole? Here's a simplified version. And the major parts of a black hole. Keep in mind that all this breakdown is theory. A black hole compressed to a point, but this is what, theoretically, supposed in reality, we have no idea. We've never seen a black hole. We have no idea if a black hole exists. So, again, this is what most physicists believe. And, well, is it actual? Is it mathematical? It's referred to as a gravitational singularity. The singularity can best be described as having a region within which the escape velocity exceeds the speed of light, defined by the Schwarzschild radius. Singularity is a point within space with so much gravity that supposedly not even light, which would be the fastest thing around, can escape. Now, how would it appear to be outside, to an outside observer? Well, it would appear as a sphere of you'd see a perfect blackness and a swirl. And at the heart of a black hole is a singularity. It's a point of zero size and infinite density. It's almost an impossible concept to digest. That's zero size, infinite density. Any object can become a black hole. But don't worry. It would take something that weighed, well, about the same as the sun. More, actually. The boundary that exists where not even light can escape the black hole is called the event horizon. So that's what you'd be looking down on, the event horizon. Or at least the rim of it. That's the last distance from which light can escape. The pole bring it down. It's sort of like a cyclone in between. Everything, including light, gets pulled in and brought down inward, getting crushed at the center. So that's what happens. It just, I got a couple of diagrams I'll show you that are up right now that shows the arrangement of the singularity and the event horizon and the Schwarzschild radius. So you can see all those. Basically, all you need to know is you've got up here an accretion disk, you've got the light can't escape from here down. So a person viewing it will only see this. That's all they're going to see. So then they're going to see you stand here forever while you go down. So Schwarzschild black holes. Well, the anatomy of that, well, that's a black hole without a charge and non-rotating. And it's actually believed that non-rotating black holes don't exist, but I believe that the Schwarzschild metric provides a simple model of what's going on in a black hole. As is apparent, there are a couple additional components compared to the basic black hole anatomy. To recap, a black hole has an outer event horizon, an inner event horizon, or a Cauchy horizon as it's known. And one side of the Cauchy horizon contains a closed space-like geodesic, and the other side, geodesics that are time-based. So a geodesic, quite simply, it's the shortest path between 2 points in a curved space. As matter falls into the black hole, it takes the shortest possible path. And beyond the Cauchy horizon, space and time geodesics become reversed. So, beyond the inner event horizon, you are no longer traveling through space, but through time. As such, if you were to cross this horizon, you would move towards your inevitable future, which is the singularity. Not a fun future. Outside the Schwarzschild radius, there's a boundary called the photon sphere, where gravity is strong enough that photons, light particles, are forced to travel in orbits beyond that boundary, and you will move towards the event horizon. But at the photon sphere, the photons will travel in orbits for at least a little while. The orbits are unstable. Well, what's interesting about photons orbiting in circles is that when you are located at the photon sphere, photons that start at the back of your head will orbit the black hole and will then be captured by your eyes. So effectively, you will see the back of your head. Weird, right? But I told you, black holes don't follow physics. The rotation of the black hole causes the Schwarzschild radius to become oblate due to the centrifugal force. Now, also the gravitational singularity is no longer a point source, but a two-dimensional ring singularity. One important additional component for the rotating black hole is the ergosphere, which is a region beyond the outer event horizon. It touches the event horizon at the poles of a rotating black hole, and it extends to a greater radius at the equator. And depending on the speed of the rotation of the black hole, the ergosphere will be shaped either like an oblate spheroid or a pumpkin shape. So, a rotating black hole, which is either a Kerr black hole, a rotating black hole without electric charge, or a Kerr-Newman black hole, a rotating black hole with electric charge. A black hole can only have three fundamental properties: mass electric charge, angular momentum, spin, stars rotate, and when a massive star collapses into a black hole, its angular momentum is not only conserved in the black hole, but as its radius decreases, so too will its angular momentum increase. Think of an ice skater who, they're spinning around, and you know how they pull in and the spin gets faster and faster and faster? Well, as a black hole twists or rotates, it twists space-time in the direction of the rotation at a speed that decreases with distance from the event horizon, meaning that space-time closer to the event horizon will be twisted to a greater degree than the space further out from the event horizon. This process is known as frame dragging. Because of the dragging effect, objects within the ergosphere cannot appear stationary with respect to an outside observer at a great distance, unless, there's always an unless the object was to move at a faster than the speed of light with respect to local space-time, which is not possible. Since the ergosphere is located outside of the event horizon, objects in this region can still escape from the black hole by gaining velocity due to the rotation of the black hole. Did you ever consider that there might be a hot black hole? Although black holes just sit there in space like vacuum cleaners, just sucking things in, well, their enormous gravity pulling things, they thus have a temperature. So what about someone falling into a black hole? Well, besides not being able to breathe, but anyway, they wouldn't notice any change. The photons given off when a person crosses the event horizon will slow down to zero by the gravity, and hence the observer will never see them disappear. Have I forgotten anything? Forgotten? No. Is that all? Not by a long shot. But I really can't explain them all. I mean, do you have, well, there are literally tons of books and just as many books and movies, and some real, some sci-fi. Black holes are really one of our greatest curiosities. And if I may, allow me to recommend one such book by Leonard Susskind, The Black Hole War, because it tells you what you need to know and what you need to look to read. I mean, as you go through it, and it explains when he was having his war with Hawking, and it's all about all that, but you learn a lot during it, but you also learn where you want to go for more information. So I recommend it as a starting point to figure out where you want to go on that. Now, I want to give you a brief rundown, simple really, of my theory of black holes. I mean, it's really simple how I'm going to explain it. I'm not, because I worked hard to get to a simple explanation of it, so you're going to get it. Basically, here's what others say with reference to a black hole. Huge gravitational pull, even light can't escape. Single point of zero volume, infinite density, and they haven't even worked to figure out what the environment's made up of, what you would be facing. That's point one. Now, whether it's water, electricity, air density, or other types of matter, they always take the path of least resistance. So, if you have a black hole and you're at the point of no return, picture a light photon. It could fight the pull, which will take tremendous energy and effort, or it can follow the path of least resistance. I do not believe that light cannot escape a black hole. I only believe that, why should it? It's going to take the path of least resistance. Now, the next thing I thought about when I was working on this theory was the black hole itself. It's like a funnel cloud, like a tornado, or water flowing down the drain, that's it. We know that tornadoes on Earth, or even space storms, have an electromagnetic component that the vortex is made up of. Charged particles, electrons, protons that have to remain equal. Simply put, regarding the charge running through a black hole, what enters and what leaves, well, it's all governed by that. So if you have 5 pluses coming in, you got to have 5 pluses here, and it's even. Now, if a 6 come in, then one's got to go out. So the tail, you have an output. Well, if you have an output, you can't have a singularity, which is something I had a problem with anyway. So let's get rid of the singularity. So as long as you have the 5 come in, 5 are here. When the 6 come in, 1 goes out down below. But if 1 doesn't go out down below, the whole thing's going to dissipate and just because the charge became unequal and it became unstable. Now, here's the next cool part. See, I have it planned where a black hole, there'll be other kinds of black holes, but this is one kind I do believe exists. Here's the edge of the universe. Here's the black hole coming up. So you've got a black hole here. Now, it's connected with an output that's not in the known universe. Now, it's going to leave things out here. Now, the charge eventually, maybe it's 10,000 years, maybe it's 1,000,000 years, gets disruptive. Now, that part now becomes, the whole universe extends from here. Now, when the equilibrium is disturbed, the whole thing falls apart, and the vacuum becomes part of the universe. So then the universe that ended here now ends here. And then a new black hole can form there. And with all these black holes that are in the center of galaxies and in the center of, this is all what I see it going towards. So if energy from a black hole were lost, that would mess up that precept. In this model, energy is freed to the expanding universe. The final area in the black hole is where the stuff comes out, be it putting together planets after you've taken maybe planet A and planet B and put them together in the hole when they were scrumbling up together. Boom! Now you got a new planet and you've expanded the universe. Think about it. Objects and gases and all that stuff that makes up planets and stars comes down and it's pulled in. What happens next? Has to go somewhere. And these are all building blocks, right? So comes out on this side, forming a new planet, new star, and this becomes part of the universe when it expands. And then the cycle starts again. Am I saying that this is the only sort? No. I'll see you next time when space-time continues.